This primary component has a comprehensive configuration template with respect to the time domain, a good candidate for dictating to the abstracted algorithms of all components how to represent time domain data during calculations in the simulation phase. Here, the pulse repetition rate is the inverse of the peak-to-peak time of the output pulse train, and in turn, this peak-to-peak time is the time window. As discussed in the help menu for the pulse diode laser, this fundamental concept can be further subdivided into the pulse and valley regions. The pulse full width at half maximum and the pulse duration entries configure some granular properties of the output pulses to be generated. Just as an aside, do not worry too much if you've missed a thing or two in your initial configuration. The multi-threaded engine allows you to analyze all aspects of the data at any time during a simulation, and for any component. For instance, if you find that the diode laser outputs something undesired, you can always restart your simulation at an early stage after making the necessary updates. The output signal has a peak wavelength of 1870 nanometers, and each Gaussian peak pulse power shall be set to 4.2 watts. By setting the overlap type to core, one ensures that this pulse train signal is automatically coupled into the core of the fiber amplifier when such a scenario is applicable. The time window is the physical time in seconds under which the output signal is discretized. The discretization can be configured under the Discretization tab. The time window is divided into two regions, the pulse duration followed by the valley duration. Each part can have a unique discretization. This empowers the user to simulate systems with high and low duty cycles within the Photonics Workbench. The resolution is high in the region where it is needed most, during the pulse. From experience, the pulse discretization ranges from 50 to 2048, while the valley duration may require a setting of 3 to 100 samples. The only limitation is computer memory and computational performance, the latter of which is inversely proportional to your discretization setting. In this experiment, the smallest timescale across all components is 1.88 milliseconds for non-radiative relaxation between energy levels 2 and 1 in the thulium fiber, as illustrated earlier in the energy level diagram. In order to resolve the fastest process for accurate results, and when running under the comprehensive mode, all time steps in the simulation phase should be a fraction of the smallest timescale value. The pulse discretization divides the selected pulse duration into time steps that should be granular enough so that the discrete samples are separated by a time step that is shorter than the smallest time scale. Now, let us take a closer look at the pump CW diode laser. The output average power of the pump is set to 3.139 watts. The peak wavelength is set to 800 nanometers, and by setting the overlap type to cladding, one ensures that pump signal is coupled into the cladding of the fiber amplifier when such a scenario is applicable. The time window is the physical time in seconds under which the output signal is discretized. The discretization can be configured under the Discretization tab. As discussed earlier, in this experiment, as the primary component, the pulse diode laser with ID1 manages the discretization and the time dynamics of all components. The settings for time window and discretization for the CW diode laser is not relevant in this case study. The purpose of the filter is to simulate Fresnel's losses. The configuration of transmittivity 1, or in other words, the transmission from left to right, is such that the pump wavelength at 800 nanometers and the signal wavelength at 1870 nanometers with 3.139 watts and 4.2 watts of power respectively are reduced to 3.0 watts and 4.0 watts. Clicking on the graph analyzer icon will open up the data file showing what is the transmittivity with respect to wavelength. Here, only two wavelengths were identified, If another signal travels via this filter, the engine will automatically interpolate the transmittivity for that signal wavelength. For example, a signal at 1 micron will have a transmittivity of 0.9557. Now we are ready to simulate. Well done, the ramping up is over. Press on the green play button to get started. To commence, click OK without checking the box to the left. We'll be running under the comprehensive mode, although the user may want to check out the help menu to learn more about preview mode, an alternative calculation process offering the user a significantly faster simulation experience but with potentially less accurate results. The Photonics Workbench will capture all your configurations from the design stage and begin generating and initializing the system. The computer memory usage starts to increase as signals such as SE or SRS are automatically generated. Once all the initial signals are accounted for and the components are provisioned, the system starts to execute each component in turn. This goes through a predetermined amount of cycles as defined by the phase manager. Now let us access some data. Although the simulation is still at 28% completeness, one can always access variable or static data from any component. Let us take a look at the emission cross-section of the fiber amplifier. The two control variables, upper energy level and lower energy level, allows one to choose all the energy level pairs of interest. For thulium, there are 4 principal energy levels. For those interested in absorption cross-section with upper energy level 1 and lower energy level 0, can do the following. Note that for simplicity, one can leave the automated suggestions in the text boxes which indicate to the engine that the user is requesting all possible permutation of upper or lower energy levels available. Next, let us access some power distributions from the database. Power, or amplitude, can be analyzed with respect to time, space, and frequency. In selecting length as the domain, we are going to be viewing the variation of signal power as it propagates down the length of a 1.5 meter fiber. At this point in the simulation, it is likely that not enough time has passed in a laboratory system for the light and matter interactions to stabilize or converge. Let us wait a little bit longer to see how these power distributions change. As you can see, we'll let the simulation run up to 90%. Let us observe the current power distributions. These results reflect accurately the results of the journal article for which this case study is based. Every component offers a database of information. The Photonics Workbench framework brings forward the most commonly accessed information, such as energy, noise factor, and so much more when fresh installed. Please do not hesitate to ask Inspired Photonics support to install other data modules as this is quite simple due to the highly extendable framework that is Photonics Workbench. We hope you enjoyed this session. For those interested in simulating fiber lasers, Q-switched fiber lasers with either active or passive switches, and more using the Photonics Workbench, please visit our website for additional training videos. If you have any questions, please do not hesitate to contact us at support@inspiredphotonics.com. Thank you for watching.